welcome everybody to the new. Bienvenue à tous pour la troisième session de la nouvelle série du séminaire de mécanique des fluides. Donc aujourd'hui, on a le plaisir d'accueillir Cesar Pairetti. So I will do the introduction in French and then I will finish in English.
Ça marche?
Donc Cesar Pairetti a fait sa thèse avec Roberto Nigro et Santiago Damian, c'est ça?
Santiago Marquez, Damian.
Santiago Marquez en Argentine. Et Roberto Nigro est un peu connu dans le monde du high performance computing. Vous avez peut-être entendu parler de lui. Il avait aussi collaboré avec Sergio Idelson, qui collaborait avec Pierre Sago. Enfin, il y avait déjà des connexions. Et j'ai eu le grand plaisir d'accueillir César pour un stage pendant sa thèse, où il m'a montré des super simulations avec Basilisk. Et donc, c'était un bon début. Et depuis, César a fait plusieurs postdocs et plusieurs séjours avant la thèse et après la thèse ici au laboratoire. Il travaille en ce moment avec Jean Robin, qui est là-bas au fond, et l'équipe d'ArcelorMittal Mézières Research sur des impacts de gouttes très particuliers. Mais ce n'est pas de ça qu'il va vous parler aujourd'hui. Il va vous parler de modélisation de la turbulence. So, basically, you have been introduced. You work on turbulence modeling. You do a lot of other things, but we don't have the time to discuss all of them. So please, you have the floor.
For sure. Thank you. Okay. So thank you everyone for coming to the talk. I will talk about this topic specifically, but there's another title. It's why is turbulence so difficult to me, at least. So I will share some ideas, and then at the end we can discuss some capabilities of developing new turbulence models related to this particular approach, which is the Pseudo-Direct Numerical Simulation, developed mainly at CIMNE at Barcelona by Sergio Idelson and Juan Jimenez. So I think they might be online. But first, before the talk diverges, because I usually diverge, I want to stress the main points of the PDNS. So the name comes from Pseudo-Direct Numerical Simulation. I will explain what that means during the whole presentation. But basically, it's a multiscale approach to model turbulence, right? And the particular feature that this method has is that it resolves, of course, coarse and fine structures of the flow, but the fine structures are solved offline. So that is cheaper, and it's kind of approach similar to ROM, so reduced order models. And it comes from a line of development related to multiscale materials. So it has a really strong mathematical support for that. That is what Sergio was doing many years ago. And now with Juan, they developed this particular model for fluids. The key of the model is related to how they developed the reduced order model. That is what I am going to explain, or at least I will try. But I am not an expert on turbulence myself. So probably I will say, I hope not to say any stupid things, but I will try to just share with you some thoughts. Probably most of this is known for you. So the main question is, why is it difficult to solve turbulence? And then you have the question, what does it mean to solve turbulence, right? From our point of view, numerical methods, maybe you want to resolve all scales. Well, that might be difficult. And from a mathematical point of view, you know that there's these Navier-Stokes equations are a millennium problem. And the thing is, the nonlinear set of equations, you have the advection term, that is the nonlinear part. But it's multivariable, so the three components of the velocity are strongly coupled. So that's why it develops a particularly chaotic behavior, which is multiscale. It's concurrently multiscale, right? So I have this example of the Lorentz system, but I have many slides, so probably I won't run it. You know the drill. You throw a few points, and they after some iterations they diverge when they evolve in time. So that is what it's called the butterfly effect, or the sensitivity to initial conditions. And this is the isotropic turbulence simulation in the Basilisk website. So you see lambda 2 isosurfaces, which is a way of visualizing the vortices. And the thing is, with turbulence, you have sensitivity to initial conditions, but also they diverge quite rapidly, right? Depending, of course, on the Reynolds number. That's why this number is in red as well, because the relation between the dissipative terms and the nonlinear terms is given by the Reynolds. So this is everything is well to you that you do fluids. And I took some examples from Luis Caffarelli's presentation in the Clay Institute of Mathematics when he was introducing this particular problem. Of course, you also know these equations really well because Navier was one of the main developers. And actually, I think it was 1 or 2 years ago, we were happy to remember the many hundreds of years of Navier-Stokes equations. And then you have George Stokes from Scotland. But what I took from Caffarelli's presentation, of course, it's an extensive presentation of 1 hour about the mathematical model and the inconsistency. And he has a really good example. He says, the problem with this mathematical model, yeah, for sure, this is 2008, and he was still using these kind of slides. So you can't really tell, but the things he said they were so interesting. He's a mathematician, so he has good imagination. I am not so good at imagining experiments. And he suggested, well, if you think a good mathematical model is like Newton's second law of movement, you get a particle, you throw it, you know initial velocity and position, then you can compute the trajectory, right? That is not the case with Navier-Stokes. So that is a way of describing the chaotic behavior. So he takes 1 whole hour to explain this, and he said, well, you can tell the equivalent to a single particle with Newton's model, it will be just having a bottle with liquid, and you put some tracers, which are actually peppercorns and garlic, and when you shake it, then you see the trajectories are not predictable at all, right? Even if you get water, it's less viscous than oil. When you do it with oil, I would use this to cook later, so that's why I did it. And then they move slower, and the trajectories are more predictable because it's more viscous, and then it's less turbulent. And of course, these tend to an equilibrium because it's a predictable system. It has the weight of the particles, so they go to the bottom. But in some cases, that is not actually what happens. If you have a constant source of energy, maybe the energy will generate chaotic trajectories, and that's what Caffarelli explains. And he won the Abel Prize 2023 because one of the reasons was a paper where he showed that weak solutions of Navier-Stokes should be bounded. That took like 62 pages and 13 theorems. So again, I am a mechanical engineer. I don't do rigorous mathematics. I usually get a different background. So Stefan discussed it briefly. I did my PhD at the University of Rosario. My advisors were Nigro and Marquez Damian, and Norberto and Santiago. And I will do this review of the background because it explains my motivation to study these kind of problems. And in particular, I was dealing with fuel injection modeling for internal combustion engines, but we were trying to tune LPT-like models. Well, usually it's called discrete particle models, where a single particle actually represents several drops to represent the evaporation of fuel on engines. And then we moved to DNS to obtain some data and try to predict atomization on the early stages. And that's why I learned Basilisk. As Stefan said, I came here 2017 to learn the code, and then I use it intensively. I should put a heart next to it, but I love it now. It's the only code I use. During my postdoctoral research, I was still doing OpenFOAM, and I was coupling OpenFOAM and Basilisk. And it was kind of a nice approach to decouple scales, because we did internal flow with one code, and then the atomization with Basilisk, which was more efficient, still is. And afterwards, I work in several other projects which are also related to turbulence. So I will try to explain why all of these projects we work with Stefan lead me to get more interested in atomization, but of course in turbulence, which is the topic today. Also, I do teaching at Rosario, and I teach a few courses in the mechanical engineering degree, fluid mechanics, heat and mass transfer, and some computational fluid mechanics, dynamics actually. It's the same, but we usually say CFD, not CFM. But the point is that some of the slides you will see here, they are taken from that course because I think it's the safest or the easiest way to explain the mathematical framework for PDNS. I hope it's true. And I am also working with some PhD students, Clara and Juan Cruz, which are developing codes for sprays and granular flow, and might profit from these models as well. So some caveats on the presentation, tools and limitations. Regarding the equations, I usually use colors to remember stuff. But yeah, and this is mostly based on the general transport equation. It is the framework I used to develop the theory during my PhD, and it stick with me since then. And I might throw some memes, sorry about that. And also I am not really good with the slides design, so please I apologize in advance. Regarding my PhD and the fuel injection, this is a basilisk simulation of a diesel jet based on the Akayama experiment. It's kind of old, but it was one of the first experiments where you could see the fungus shape on the injected fuel, which is reproducible by the pulse jet benchmark that every basilisk user knows probably. And so this was an interesting case. I tuned the surface tension to reproduce that kind of range of droplet size. Hence, the Weber number was quite higher, and that's why you get a wider range of scales related to the interface. And we did some statistics on that based on the volume-based diameters and the surface-based diameters as well, measuring deformation and the mean Sauter mean diameter. And of course, some of you have seen the Yash presentation on the pulse jet closer to the, closer to the benchmark setup, which has larger scales, and it's quite nice because then we can develop manifold depth there. So to mention some other developments that we were working with Stefan. But in this case, I wanted to show that it rapidly breaks up into really small drops because you want to evaporate the fuel. So that's the main goal, to increase the surface density and have a really, really small scales. And that is really difficult to get, of course, you know, because the BOF limits to represent the interface. You have only one plane on each cell, and then you need a huge number of cells to reproduce a really thin structure within the whole jet context, right? It's like 1 to 1,000 range of scales, and that is quite expensive. We did some statistics regarding the curvature, so you see that the high curvature is related to small scales, small drops, and you can see how the sheet perforation works near the head of the tip of the jet. And what does tell us? Well, it gives a lot of information regarding how grid resolution affects the interface representation. It doesn't say much about the velocity field, right? So we weren't looking at turbulence at that point, but of course, the formation of the liquid structures comes from the velocity gradients as well. So you really need to also represent the range of scales for vortices and that much. Then I will cite again Yash presentation regarding how manifolded was using the pulse jet to say that we are still working on the grid conversions for statistics. So at that time, 2019, we didn't have manifold depth. We just tried to do grid conversions by DNS and single wolf plane on each cell. And then we were trying to cope with the lack of computational power, just looking at the volume fraction. So trying to reproduce only the surface density. That was an approach that led us to say, well, if we keep increasing the grid resolution, we get the same area, then the evaporation will be the same. So this we could use for engineering, but still it's quite expensive. And we weren't looking at, again, the velocity resolution. Even using the AMR strategies based on the numerical error, which is implemented in Basilisk in the adaptive wavelet. but what we saw is that those two parameters, how you tune the IMR, affected not only the size of the drops, but also the spatial distribution, right? So again, that it puts a focus on how well you resolve the velocity field. And as I said, this was quite expensive, and at some point you want to develop these kind of models to represent the fuel injection on an engine. So those are particles, and the particles in the DPM are supposed to be spherical. And that's why we moved to a secondary atomization case, which is a single drop. And we study how the modes evolved for that single drop to develop the sheets. And that was also part of my thesis, and also the undergraduate thesis from Patricio Canciani. We were studying this single drop experiment, only looking at the Reynolds and Navier number. That is the Reynolds-Nichols characteristic time, so everything is dimensionless. And then the takeout of comparing the jet simulations with these simulations is that the same mechanisms that are present in both cases, which are multi-phase flow and they are turbulent because of the Reynolds values, still you don't see all the breakup mechanisms in this case, which is within the smaller range of Reynolds and Navier numbers. But you reproduce, for example, the weak spots that are formed in the sheets, which is something that we want to study on atomization, and we want to analyze only that kind of approach. The same thing happened with the ligament paper that has been recently published from Sagar's fall thesis, also in this university. So again, this was some sort of decoupling scales. From the pulse jet, we took a drop within the range of parameters which we saw in the full atomization case, and we tried to analyze what is happening only to this particular sub-range of scales, right? And we got a statistics on that, and then we could filter out again the sub-ranges within the sub-range. So it's some sort of multi-level approach we did. And that was one way of decoupling, multi-level, but then you have different processes. For example, in agricultural sprays, this was the first postdoc I did on CFD, trying to analyze how far would agricultural spray drop fly, depending on the temperature and humidity and that kind of stuff. So we used OpenFOAM for the internal flow because we had a geometry already meshed. And then Basilisk for the atomization. So it was quite interesting to couple different codes. And afterwards, we did a simple 0D model to predict the flight, the trajectories, right? Just with the statistics of this detailed CFD. So again, this shows how decoupling scales and decoupling phenomena or regions of the phenomena help you to reduce the computational cost significantly, right? And for example, we ran the stationary nozzle simulation and coupled it with the atomization because we supposed and we verified with experiments that the flow within the circuit, the hydraulic circuit, didn't change that much. And then again, we validated this with an industrial partner. So moving forward, 2020, COVID was everywhere. And it was also here. So we collaborated with people at Twente University, where they have these channel experiments that we reproduce in this paper from 2021 with pallet count at Twente indeed. This is Basilisk again. And the good thing, there's a parallel between what I've shown from my thesis and this. You see in the cough, in a real cough, you have a lot of small structures from the whole respiratory system, and they have several modes of breakup, and it's quite turbulent, and it depends on the Reynolds, which is quite high. In this experiment, we could control the airflow, so we could reduce the range of scales and just analyze what is happening with a single weak spot and a whole expansion, which is analyzed in different experiments. But then this is a good way to, let's say, to represent this kind of phenomenon in a setup which is closer to the actual problem we wanted to study, which was airborne diseases. And finally, you can get even more complex. So if you increase the phenomenon you consider in the fluids. For example, this case was compressible simulation of a liquid metal. So this metal gas atomization is one particular way of getting metal powder for 3D printing, for example. And this is a work we presented in iClass this year. So the idea was to use DNS again to try to reproduce the PDFs near the nozzle. So we can, afterwards, we could use that statistics and try to predict the actual PDF of the powder after frozen the liquid metal drops. And usually you get this approach where they use ELSA to just tune up an algebraic model. And then you can design different nozzles based on these kind of relationships. But these relationships depend strongly on the adjusting coefficients. So having the whole range of DNS plus turbulence models, which include the multi-phase phenomena, and then trying to fit these kind of relationships, it was a kind of motivation to get into turbulence models. Rand's approach doesn't work that well for the moment, according to people in San Sebastian, but they were moving to LES. So that's why probably we are going to discuss LES in more deeply today than Rand's. But then I think that my motivation during this, it's been more than 5 years now, working with these kind of problems. It was atomization, but we were focusing on the interface dynamics, surface tension. Now I wanted to focus on turbulence. So how could we deal with the turbulent flow, and how could we resolve whatever it means, the velocity field? I mean, whatever it means. Of course, in AMR, you set up a critical threshold on the estimate of the velocity error, right? And then you say, well, I am resolving this up to this point. In the context of turbulence, usually you say, well, I am not sure if I am representing correctly the energy transfer between the subgrid scales and the scales I am actually representing on the grid. So that is what I want to discuss today with you. Also, I saw that the decoupling scales is really useful in several industrial applications, mainly, which if you try to tackle with DNS, of course, it will be too expensive. And probably it will be expensive with LES as well. And the transition regimes are also interesting. As I said, in the Kauf machine experiment, we reduce the Weber number and we keep increasing it and checking out how many modes you get within the thin sheet and how the weak spots evolve in those transitional regimes. So, some have a way of presentation. Yeah. But for today's presentation, I will focus on single phase flow to get a common ground to develop different models, which is usually useful to scale it up to just tune a particular aspect of the model. This has been the case for Rand, for example. You see the K epsilon, K omega, and then it keeps scaling up. But it's also good to have a general mapping between Rands and LES. That's what I'm trying to discuss today. And again, it's a numerical method-based approach. So that's why I will use the basic slides from my undergraduate courses. General context, again, what is turbulence? I think that we saw this isotropic turbulence simulation. It's a chaotic flow based on the nonlinear term evolving in time. We are not mathematicians. So how did we study turbulence during through history? You got Reynolds with the pipe experiment and front and boundary layer developments. And nowadays, people using DNS to analyze what is happening in the boundary layers. These are two simulations taken from the Gallery of Fluid Motion from APS. And these are quite old. Both cases are, again, the lambda 2 criterion to visualize the vortices based on the second eigenvalue of this tensor, which is based on the velocity gradient. So for us, it's quite well known. And you try to reproduce the behavior of turbulent flow by these numerical methods, numerical simulations, mostly spectral methods. It's also the case in the isotropic turbulence. The reference is a spectral code. But now we are going to try to use FVM, finite volume, and I will explain why during the presentation as well. We described the mathematical framework from some presentations. And regarding the experimental analysis, I won't get deeply into that, so we can take more time with the numerical methods. But I will mention briefly the developments of Richardson and Kolmogorov and the Kolmogorov theory from papers from the 40s and the 60s, and energy spectra based on the, well, you can put it as getting the Fourier transform of the velocity field to see how the energy is transferred between scales, between the small vortices, which are characteristic of dissipation, and the large vortices, which are the ones related to the geometry of the flow, the largest size. So I put this picture from the video because they discuss how the 5/3 comes up in this graph, and they discuss if it is a universal constant, such as the speed of light. And they also describe quite nicely how the stretching and deformation and breaking mechanisms of the vortices explain the trend of the energy spectra. So this is quite a nice reference from 3 Blues 1 Brown. But again, this video is like 30 minutes, and I only have 15 more. So this is another interesting video, but Steve Branton has a huge load of literature on machine learning for fluids, so it's data-driven models. In this particular video I am citing here, he takes the Feynman lectures and he explains transition to developed turbulent flow. And again, it's the same framework we were analyzing with Caffarelli's presentation. And I really like the explanation he gave regarding how we transition from large vortices to the small ones for dissipation. But then there are like 7 hours of course in YouTube where he goes up to the point of explaining how could we use machine learning to actually model the small scales. Anyone familiar with LES or RANS, you know, you need closure terms, and those are the ones he usually tunes with data-driven models or mainly machine learning. Why would we like to use numerical methods to study fluids? Of course, in particular turbulent fluids, because when you try to do these kind of experiments, this is not turbulent, this is less than 2000 regarding Reynolds. And you have the collision of 2 vortices, which are really difficult to generate because you need a constant injection rate. And then you have to use the ink to visualize the flow. So this guy, he was a NASA engineer, and he was working a whole year to develop this experiment and get these shots. These shots were the best. This case was simulated by Anton van Hooft, and it's in the Basilisk website. And so he was using particles to do the tracer in the simulation, and you can see the adaptive mesh refinement on the bottom. So these simulations are quite cheap. You get the Reynolds number there. You can finely tune the Reynolds number. You can see the transition between regimes that we were discussing before. So again, this is a much more controlled kind of experiment. For these cases, it's reproducible. When you have sensitivity to the initial conditions, then reproducibility is quite a nice feature to have. So that is the main advantage of numerical methods that we all know. Mostly of the people in the room are using Basilisk or any other code. But then with turbulence, I feel I am doing something like this, right? So I want to study turbulence. Okay, you need to know fluid mechanics, mathematics. Here, if you don't use CFD, okay, of course you don't need that. But usually this is the first meme I put in my slides for students in the undergrad courses. I feel a bit like this studying turbulence. So I am trying not to skip any steps, and I don't want to do colorful fluid dynamics, which you might say up to now it didn't show a lot of equations. I want to do careful fit of data. So first I want to know what is happening in the computer when I'm running the code, right? Of course, I know theory of CFD. I haven't using it in a black box matter. You have the model from continuum mechanics, and use any method to discretize the equations. In particular, I will explain finite volume method because it has a really nice parallel with the theory of fluid mechanics you usually use to analyze mean values. So if you want to filter out some range of scales, you could start with the mean value. Actually, that is what the Reynolds-Averaged Navier-Stokes does. And so that is a good feature that the finite volume method and these turbulence models share. But the PDNS paper I was citing at the second slide, it's also based in finite element methods. That's why at the very beginning I skipped it, but we are going to get back there. It talks about representative volume element, right? Because if you work in the finite element method and you have the integration tools in that context, you want to do an element that let you represent what is happening in the subgrid scale. So what I was saying about the finite volume method is that you can pose the differential equations in terms of volume integrals to get the mean values, and you get this kind of decomposition where you have some values you are going to compute on the volume, some values you are going to compute on the phases. So that is what Basilisk does with phase interpolation schemes, usually BCG. And you have the source terms also that you need to integrate, and you have a mean value. Gravity, for example, is a constant, of course, but then you could have more complex phenomenon like heat source that is depending on any other variable. So that's when you get tricky, and this term, which is the advection term, is linear for a general tracer, but it's non-linear for the velocity. So you need to linearize it. I won't get into the projection method that is implemented in Basilisk solver, but I will put a general transport equation, and usually for this 1D case, I am explaining this. Of course, I am not explaining this to you. You are all familiar with this. But what I want to highlight here is that this way of getting the mean values and separating the fluxes and in particular these stress terms, here is only the diffusion, but the general stress term could be used to actually get a closure on what is happening within the cells. That is what usually you do with LES. And so the thing is that with numerical methods like this, you get a linear system, applying all the approximations for the fluxes on the phases, and you solve that linear system with any iterative methods, and it's quite efficient. So that's why you can go until several thousands of millions of, well, actually it's billions in English, cells, and then you can get really refined near anywhere you want to reproduce the whole range of scales. But still, it's expensive, because if you keep increasing the Reynolds, the computational cost for uniform meshes increase with a power of 9/4. So even if you want to do Reynolds 5000 for a large enough domain, it's quite expensive. That's why we usually represent turbulence scales with models. I've been discussing up to now the DNS, so not using any closure model at all, not using anything related to the mean values of the finite volume method. Of course, that is the most expensive approach. As I said, this has 3 billion cells. This is the simulation of the LineFlow Center, 2015. But if you want to run any simulation in a laptop or a workstation, you can go that high. Nowadays, you can do 1 million, say, maybe 10 million, I don't know. But so if you lose those 2 orders of magnitude on the cells, you might want to move to LES or runs, which are representing what is happening within each cell with a particular closure model. The idea that's running this kind of modeling approach is, well, I will resolve part of the flow. In runs, it's actually not a range of scales, but just the mean flow, so the most basic range of scales. And then everything that is happening within the cell, I will represent it with something that should behave like turbulence scales within the cell, right? So runs, in a nutshell, it's these 2 blocks. I won't speak anything else about runs from now on. but this is the Navier-Stokes equation for the mean value of the velocity, which is the u. You see here the decomposition between the actual velocity field, the mean value, and the perturbations that comes from turbulence. So the effect that the perturbations had on the mean flow is actually given by this term when you run the Reynolds averaging process, and that is relating to the mean value of the perturbations. So it's a way of representing the momentum that comes from the small scales into the mean scale. And Businesq posed a way of modeling this based on the deformation tensor, but you could use more complex models to do that. And Prant suggested to estimate this turbulent viscosity by a mixing length. But as I said, you can use more sophisticated models like the K epsilon. It has two transport equations that tell you how the turbulent kinetic energy, which is K, and the epsilon, which is the rate of dissipation of energy, of turbulent energy, sorry, how they are transported through the flow because of the mean values of the velocity field, and how they are generated and dissipated, which is related to the Kolmogorov energy cascade we were discussing before. So everything here is theoretical, and it has some strong assumptions, some strong hypotheses that make this model suitable for just a specific set of cases, right? This is not universal, so that's the point. And then that's why you see that there are more than 100 RANS models. It's not only K epsilon or K omega, but then you need special treatment for the wall flow. You need special treatments when the flow has swirl because the vortices break up in a different manner. A different approach is LES, which it actually uses the fact that you are using a mean value of the flow, but mean in the sense of averaging within the cell. And there you consider that you are actually just filtering out some part of the energy spectra based on the filtering scale, which is here delta. This is for the finite volume method. If you don't use anything, you are using the mean value of the fields within each cell. So you could say that you are using that kind of filtering because the filtering definition is like that. This is the volume mean value. So when you do DNS with finite volume, and you don't put anything as a subgrid tensor, you are doing something like implicit LES, which is considering that the numerical errors you have on each cell, they are more significant than the actual stress tensor, and then you don't need to add anything. Other options which are explicit LES are Smagorinsky or modified Smagorinsky, Germano. There are a lot of closure models that takes into account the Kolmogorov theory for isotropic turbulence. Again, this is not general. You can't reproduce the turbulence close to a wall with this kind of approach. But those are based on theory, right? I mean, verified theories, really good theories. But again, if you try to do this, you really need high order methods. So you reduce the error, the numerical error, I mean, as much as you can. And it might get quite expensive. If you use coarse grid, you still have a large numerical error. So during my thesis, for example, I was trying to compare different refinement strategies. The one on top is actually Basilisk adaptive wavelet. So it estimates the error on the velocity field and tries to limit that based on so it gives you a criterion based on this estimate of error to say if you are going to refine or coarsen the grid. So blue regions here are coarse grid, and the red regions are finer grid. Doesn't matter the exact value of the level. Those are level 12, I think. But the point is that if you see now, these are the vorticity fields, and this is the standard Basilisk. So you see that close to the cylinder, the behavior is quite similar. But then here at the bottom, you see that the vortices live much longer, right? So they are preserved in the simulation. That has a cost, of course, right? So it's refining the grid much more because this kind of approach is based on trying to estimate some Kolmogorov scale locally based on the rotational value of the velocity, the rotor, and comparing it with the grid size, which would be like LES filter, right? So here you try to avoid filtering out anything. So this would be something like DNS according to Pope, right? In the book of Pope, it says the grid size on your simulation should be less than 2 times the Kolmogorov scale, right? And this was an approach to refine the grid, so you ensure that through the whole domain. Again, this is not general. This will be only suitable for Navier-Stokes. That's why we always want to still use a half wavelet, because this limits the numerical errors of any field. Any primitive field will be good. But this let us play, and you can say, well, I want to do DNS, or I don't want to do DNS. I want to lose some structures within the grid, because I will use some closure model to get what is happening within. And then we get back to PDNS, to pseudo-DNS. So I was telling you at the very beginning of the presentation that you could, for example, have a coarse grid intentionally and try to reproduce what is happening within each cell with the representative volume element, right? And LES, usually you don't do this. You just say, well, the mean flow here has these features, so probably within each cell, it will be behaving like this, according to Kolmogorov theory. But that is one model you could use. You could also use a reduced order model, which probably will have the same decomposition, the coarse part of the velocity field. Coarse means the representation within the grid you are actually running, and some fine part which is happening within each cell. But instead of using a closure model, LES or RANS, you use a set of fine scales simulation that you've done online, and you table those with any kind of method. You could use machine learning, you could use neural networks, you could use any other reduced model approach. So you get this kind of tensor values. Actually, these are the components for the closure tensor taken for an isotropic case. Actually, it's not an isotropic case because the very beginning was with a shear stress, which is parameterized based on this gradient value with the boundary conditions which are periodic with the jump. So everything that I'm saying now, it's quite extensively explained in the review paper. I said it at the very beginning. I will say it again at the end. It's a paper that it's already available. It's Idelson, Jimenez. It's an overview on PDNS. But the setup is quite similar to this one, the isotropic turbulence, where you have a source term that it keeps adding energy. So you sustain the chaotic behavior. It doesn't dissipate eventually. So you get a regime which is transient-like, right? But it's still breaking up vortices and getting new structures, and the energy is transferring from the small scales and the large scales. So all of that behavior, if you want to reproduce it in one single cell, you can just map a smart tensor for the closure term, like in LES, and that's where you have PDNS. So in the paper, you can read out several validations, one with isotropic turbulence, which is similar to what I was showing before. And they use really coarse meshes to reproduce that behavior. And this is Poisson flow, but it's with a large Reynolds, so it should develop a turbulent boundary layer. And with PDNS, you see the red dots are actually the cell centers. So you are reproducing the actual velocity profile with just 1, 2, 3, 4, 5, 6 cells within a diameter. If you use under-resolved DNS with the same amount of cells, you see that you are actually misrepresenting underrepresenting the shear stresses. And again, then after you have the database, which is already stored and it's accessed efficiently, so you only get a reduced order model. You don't see all the degrees of freedom within each cell. The simulations of PDNS with 6 cells, they run in almost the same time as the under-resolved DNS, right? which is the things you usually want to with a turbulence model. But as I said, you got these wall flows, and that is Jose Weisfred. You know him from PMMH. He has this experiment where he's usually looking at what is happening near the wall. So near the wall, you have some, you have some velocity profiles that develop. This is a Couette and Poiseuille flow that develops near this middle belt. But actually, he's using PIV to see what are the velocity fields on the plane of the belt itself. And these plots are actually the values of the perturbation components of the velocity field, right? So the deviations from the belt velocity, which is actually the thing moving the flow. And you see that even if you're close to the wall and the Reynolds number is quite small, you get some patterns which are related to chaotic behavior. This is not chaotic, it is stabilizing. But the point is, these are not isotropic, right? And Kolmogorov theory was isotropic. So that's why PDNS now it's moving to, let me check for the paper itself. So you get these kind of representative volume elements where you put a boundary condition representing the wall in one element, and then you put a different boundary condition here, and you try to reproduce the behavior of the boundary layer, right? So I wanted to check the particular paper because it's much faster to move through the validation cases, and you actually see the comparison with LES. I think, yeah, this is the backward facing step case that here the wall effect will be quite significant, so you can't reproduce this without those kind of representative volume elements. So coupling with that kind of modeling will be quite interesting, especially with experimental results. Yeah, so I think that's time, and I am just throwing these recursive and recurrent reflections. Here you have the G, R, I am just using 3 R's. So these are some questions for me. I am sure that I know why it's difficult, turbulence so difficult to solve. Well, Navier-Stokes still is not completely studied. If someone finds the analytical solution, it gets $1 million. And measurements might be intrusive and expensive. That's what I learned from Jose experiment. And the thing is that you have many relevant degrees of freedom with strong scale interactions. So that's why we were suggesting this turbulence modeling with the subgrid-scale. And nowadays you have neural networks, machine learning, but other tools like GPUs, for example. So it's freshly developed in Basilisk. It would be really nice to run these kind of simulations in GPUs, for example, to expand the database and of RFVEs. That's the first point for Clara's Cortizos thesis, which is modeling sprays. So for now, we are going to model only turbulence. So she doesn't have the same problem I had running the multi-phase, the turbulent multi-phase flow simulations. But then it would be nice to integrate that first as a tau for subgrid scales in the LES approach, and then in a more refined PDNS way, which actually takes into account the advection, and it lets you play more with the actual transport of the subgrid terms based on these data-driven models. Then, if you have in Basilisk something which is AMR that might use LES with the tau CGS, then you can use a multi-level, right? So you could keep using the databases to solve new RVEs, and that will be a multi-level approach that is explained in the Sagot's book. As I said, you can use IMR in this kind of thing. Then your insights, the experts are welcome. So I keep thinking on those stuff. I am a bit confused still. Thank you very much for your attention, and well, I am happy to take questions.
Okay, so now it's open for questions. I see there are no questions online. Mm-hmm. So maybe questions from the room. Stefan?
Yeah. Uh-huh. Uh-huh. Yeah. Mm-hmm. 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 Uh-huh. Uh-huh. Mm-hmm. Mm-hmm. Yeah. Mm-hmm.
And that is going to be the criterion you use for adaptivity, right?
Yeah.
Once it's anisotropic enough,
Mm-hmm.
or another criterion based on your model of turbulence,
Mm-hmm.
then you can stop refining, right? Because your coarse,
Yeah.
your subgrid-scale model is a good one.
Mm-hmm.
So there are many interesting questions related to that, and I don't think that many people are thinking about them. Because people think that, for example, AMR is useless for turbulence because there are fine scales everywhere, which
Mm-hmm.
is not true.
Mm-hmm.
There were fine scales everywhere in turbulence, then turbulence wouldn't be turbulent, right?
Yeah.
It would be a solved problem.
Yeah. Yeah, indeed.
So that's precisely the point, that there is not fine scale everywhere.
Mm-hmm.
So I think there are, it's more common, but there are many interesting questions on these things here.
Mm-hmm. Thank you.
There was Jacob, then Maurice.
Very simple question, but what are the parameter in the PDNS, what are the actual parameters that go as inputs into the models? Like, it's the large scale deformation tensor. It's
Yeah. So that's why I was speaking about that too fast. So you parameterized the mean flow characteristics with this G gradient, right? Which is a kind of G you're applying to the representative volume element. And then with the values of G and some rotation operations, you can map that into the values you already run the simulations for in the fine grid, right? So that's the way you get into the subgrid scale modeling. So it's only based on the mean values of the flow and the shear that it's applying on the cell. Which is different when you have the wall, right? That was the point. So you have to use a different database.
Well, in a way, it was the same question I had, because so you are not using Smagorinsky, you're using something different.
Yeah.
And could you be even more precise on that? Because as I understand, you're using an ODE to. So what is this ODE comes from?
No, it's not actually the ODE. Sorry. You run a set of DNS for a single cube, which is subject to this shear stress. So you parameterize the mean flow value within the cube, and you run a set of shear flows which are characterized by this ID value. The ID value is basically the Reynolds number, but using the shear value. So when you run the whole range of IDs, which is actually like mapping the range of Reynolds you will have in the flow within each cell, you get the mean tensor value, which is the closure term you put in the mean flow equations.
Okay.
Right.
Okay. I understand.
That is the way you actually model the subgrid scales.
Okay. Thank you.
Having a table of these shear flows.
Yeah.
Yeah.
In this table, you have an entry which is the characteristic of the flow, and an exit which is output which is
Yeah, indeed. Instead of having the formula as Smagorinsky, you would have just the table.
But
Right.
your cube is periodic, I suppose.
There's a jump condition on the velocity and the pressure fields. Yeah.
Yes, but about the shear, you just
Besides the year, yes, it's periodic. Yeah, indeed.
okay.
Yeah.
Okay, now I understand.
Thank you. Thank you for the question.
Okay. Yes.
Thank you for the presentation. I actually have two questions. The first one would be, I don't really get the fundamental difference between pseudo-DNS and an LES with kind of a tabulated turbulence. This is what you explain, I think.
Yeah. Well,
Because I mean, to me, it kind of feels like LES already.
kind of feel like LES. Yes, the fundamental difference is that here, when you are doing the decoupling between scales, you are supposing that this scale, which is the one you are representing on the grid, which will be the filtered range of scales, is affecting everything, in particular the fine scales.
Okay.
Right? So that is the different hypothesis you do with RVE. And I didn't explain the detailed mathematics on how you obtain the closure term.
Yeah.
But then you get a closure term which is not the very same you get with LES.
Okay.
Because the difference is that the way you are doing the filtering is not actually only the mean value. So the filtering is different.
Okay.
And then the dependence on of the closure tertiary is different.
Okay. So do you think it will be a big, a lot of work to kind of include that in LES, as you explained in the conclusion?
What do you mean? No, actually, if you have the database, then you could do something which is like a LES closure, for sure. Okay. But then this is more powerful in the sense that this was developed in the framework of particle FEM. Particle FEM does advection with particles and then diffusion with finite element methods. That was developed in CIBNE by Sergio and Juan and other people. So they profit of having an LPT-like to advect, and then they could advect the representative volume. So that's why you don't depend on the linearization of the flows within the phases. Sorry.
Okay.
Yeah.
And second one, you had chemical reactions in red in your conclusion.
Yeah.
So what about that?
Yeah, what about that? That's really nice. So the Clara's thesis, which just started this year, maybe 4 months ago, it's actually generating a platform for general multi-phase flow with different transport phenomena. And at some point we were working with, I didn't say that, but in Argentina we were working with the YPF, it's YPF. It's like Total, but in Argentina it's a state company. And they were developing fuels based on these kind of simulations. So at some point you want to couple these subgrid-scale modeling with transport within the cell to reproduce the chemical reactions within. In this case, combustion, but it could be everywhere. Everywhere, no, any kind of chemical reaction. Yeah.
Okay. And have you found any? Sorry.
Sorry.
Ask the question directly.
Huh?
It was just to know if you found some special problems about including chemical reactions in that framework.
You increase complexity because you have the source term, which if it is depending on the flow field, because you have the interactions between the reactants, then you need to actually give some information of the turbulence model to the chemical reaction solver, right? So that is done in the isotropic turbulence tutorial in Basilisk. You have the Breman LES model developed as well by Antun and Stefan. And then you see that you could compute a diffusion for the subgrid scale diffusion for transport of any species, right? It will be something like that, but again, with species that will react with each other.
Thank you.
Trying to slow down the questions or to limit the question, because I thought that the people who manage the the diffusion, your YouTube diffusion would come back and want to close things, but they are.
Okay.
Oh, you're the one who is doing it?
I just have to.
Oh,
Okay.
you're the one doing it. Okay, so you're not in a hurry. So maybe we can ask one more
Okay.
question.
Question is again the question I had. So I'm following the idea. It's true that if you are in periodic, it's your circulation inside is particular, actually zero.
Mm-hmm.
So, but in the real DNS, or real DNS,
Mhm.
the vorticity mean is different. It's non-zero, and it could be all kind of numbers, right?
Yeah, yeah.
So you should add this to your model, right?
Yeah, yeah, indeed. It should be one of the parameters to get into the database, the circulation. This is now handled by this G, which is based on the shears you put on the RVE. But indeed, I mean, maybe circulation is a different way of describing non-isotropic cases. Because again, the RVE are not isotropic cases, right? This is the reference case for basilisk, but the database is much wider, right?
Yeah.
I mean, the RVE won't have the zero circulation necessarily.
Okay.
Hmm?
Now I'm done with this question.
Okay. Thank you.
So I have many questions, but I can meet you every day, so I don't have.
Okay.
I won't. Yes.
It's based on, I mean, it's inspired by solid mechanics, right? Homogenization.
Yeah,
solid mechanics.
homogenization of,
Yeah.
yes, indeed. So that was the original framework.
So the question is, do you have the same problem they have in homogenization? Is that you assume that you have two scales, right? And finding the two scales is actually a problem in itself.
Uh-huh.
You know, when can you apply homogeneous? You know, when is it homogeneous enough that you can apply?
Okay.
So what's the size of the RVE, if you want?
Yeah, indeed. I understand the question. I wasn't there working with Sergio when he developed from the material science these methods. So I'm not familiar with that kind of problem. You have, but it's basically the transition between scales, right? So this, if I recall correctly, it says that it's developed to take into account concurrent multiscale problems. I think it has to do with similarity. So you could use multi-level, but I don't know what particular feature of the way they post it address these transitional scales. Indeed, we were discussing last time I met with Axel, which is dealing with wall elements. We were discussing how to deal with that problem because you have the boundary layer and you keep developing, and at some point it takes the whole RVE. So that's related to the RVE size, and then yeah. But I'm not actually in touch with that part of the model. Mm-hmm. Yeah, I agree.
So I want to finish with a joke. You know, on social networks, sometimes they post things like, "Say what this is, wrong answers only." And so here you said the Napoleonic tradition of French science. So wrong answers only. Okay? So first wrong answer, you work with Sergio Ildefonso, who worked with Pierre Sagot, who developed the RVE. So mentioning Pierre Sagot, now I understand the mention of Napoleonic tradition of French science. Okay. Another wrong answer, there's a tradition in this lab. Henri Caban, who was one of the founders of this lab, has actually published a paper on a scientific contribution of Napoleon that was published in the Academy of Sciences like 200 years ago. So what else could be the Napoleonic tradition of French science? You're very dynamic. That's a third. Maybe you are almost militaristically involved in everything you do. You have give it a lot of energy. So yes, you have another wrong answer.
Well, maybe I need a better hat. I should have a hat for the presentation.
Answers. Okay.
Yeah.
So maybe you can give us the right answer. What is Napoleonic tradition of?
No, it was
French
just a joke because it was a Napoleonic. it wasn't actually Napoleonic tradition of science. It was the Napoleon era, the Diacols and that.
Okay.
But I no. Yeah, revolutionary style.
Well, they call it's interesting because they call started under the king, called the Ponts et Chaussées, inspired by the Chinese system, as I said many times. And then it continued during the revolution, and maybe there was some schools during Napoleon. Okay, so now we know what was the Napoleonic.
No, it wasn't. Okay. Now I know.
Okay, so we thank you again for the answer to all the good and stupid questions. So, next sector is